Hello guys, can you hear me? Please, somebody confirm if you can hear me so that we can start discussing the problem. Why my stream is not in here anymore? In here anymore. Okay, I guess everything should be fine. I've seen myself. So let's start talking about the problem. How was the contest, guys? Problem C. Problem you didn't solve problem C. Well, I see. I see. Okay, we discussed all those problems. How many problems you guys solved? I solved from A to F. Yeah, I solved from A to F. I wasn't as fast as I wanted to be, but yeah, it wasn't very bad. So let's talk about the first problem. Well, the first problem, there is a bottle of disinfectant that can disinfect exactly M hands. And aliens come one by one to disinfect their hands. The alien number I has HI hands and wants to disinfect all of their hands once. How many aliens can disinfect all their hands? And by the way, guys, let me tell you an important thing. We have started for our live streams because you wanted that. We are trying to add timestamps to our live streams. So from now on, all our live streams will have timestamp. You can see that which interval is for problem A, which interval is problem B, and so on. And also in the description, you can find the solution, the links of the solutions, because many of you asked for this. We decided to add that to our live streams. So from now on, you can have it. So okay, about the first problem, well, this looks like a very easy problem. We just iterate over all the elements, and the first time that we didn't have enough disinfectant to disinfect the next alien's hands, we report that as our answer. So we just see in all the values, if a of I was greater than m, m becomes 0. Otherwise, m minus equal to ai and ans plus plus, and at the end you want ans. Okay, shall we move on to the next problem? I think this problem doesn't have any further discussion. We just need to say that each time if we had enough, I mean m, if ai was greater than m, then m becomes 0 because we run out of disinfectant. Otherwise, we subtract that, add ans, add 1 to ans, and see. Yeah, you're right. We can also do it without an array. You're right. We can also assume that we just see in x. I could just here say int x, see in x, if x was greater than m equal to 0, else m minus equal to x and so on. Yeah, this would work as well. This is again a correct code. Yes. So shall we move on to the next one? Let me make it. Okay. So about the next problem. Problem B. You are given a string S consisting of lowercase and uppercase English letters. The length of S is odd. If the number of uppercase letters in S is greater than the number of lowercase uppercase was greater than lowercase, convert everything to uppercase, otherwise convert everything to lowercase. Well, first we need to know that how many lowercase and how many uppercase do we have, and then convert everything to that. Well, it's just enough. This problem is just pure implementation as well. It doesn't have much algorithms. We just need to say that we first count how many lowercase do we have, how many uppercase. If S of I was between lowercase a and lowercase z, we say a plus plus, otherwise b plus plus. So a is the number of lowercase letters, b is the number of uppercase letters. And we know that when we are talking about characters, we can compare characters as well. For example, if S of I is greater than or equal to small a and less than or equal to lowercase z, then S of I is a lowercase letter. Okay, so this if is meaningful. So this way we can count how many lowercase letters do we have, how many uppercase letters do we have, and then there are some functions that you can convert everything to lowercase or uppercase as well. But we can also just have a for, and if this was uppercase, we just say S of I minus capital A plus lowercase a, small a. This way we will convert this specific letter to a lowercase one by subtracting capital A and adding lowercase a. And in here, by adding uppercase a and subtracting lowercase a, we make everything uppercase. And then see out S. And that's gonna be all. Is it clear? Shall we move on to the next one, or do you think we can discuss more on this problem? So I guess oh, cool. What is the code that can solve it in one line? If you want, you can copy that one line code so that everybody can see. Okay, next problem. For a non-negative integer k, we define a k-level carpet as follows. Oh, I see. This problem. A level 0 carpet is a 1x1 grid consisting of a single black cell. For k greater than 0, a level k carpet is 3 to the power of k to the 0 to the power of k grid when this grid is divided into 3 to the power of k minus 1 by 3 to the power of k minus 1 blocks. The central block consists entirely of white cells. The other 8 blocks are k minus 1 carpets. You are given a non-negative integer n, print n level carpet according to this specific format. Okay. Well, first of all, n is up to 6. So, and we have 3 to the power of n rows and 3 to the power of n columns. Well, when n is equal to 6, 3 to the power of n is around 3 to the power of 6 is around 700. So first, it is good to know what is our maximum dimensions. That helps us to find out if our order is good or not. So the dimension is gonna be at most, let me also check it here, 3 to the power of 6 is 729. Okay, so it's around 700. Now let's see what is going on. Let's consider, when we are talking about 3 to the power of something, it is good to discuss everything in base 3. Base 3 really helps us to get some intuition about what is going on. Okay, so when we have power of n by 3 to the power of n, it is good to talk in base 3. So let's see what is really going on in here. we know that when we have 3 to the power of k by 3 to the power of k, and we split it into 9 parts of 3 to the power of k minus 1 and 3 to the power of k minus 1, we have 9 parts. We say that the middle part is entirely white. So what we can say is that all these numbers in base 3, consider all of them are n digits numbers in base 3. All of them are n digits. These numbers start with digit 0. These numbers start with digit 1, right? And these numbers start with digit 2. And the same for these columns. These start with digit 0, these start with digit 1, and these start with digit 2. So the ones that are entirely, for the ones that they are entirely white, which is this part, it is the part that both of the numbers start with digit 1. So if you consider cell I and j, cell number I and j, if I and j, if you consider them as n digit numbers, n digit ternary numbers, n digit numbers in base 3, we can say that if both of them start with 1, then this part is white. Hi Sam, how are you? If both of them start with 1, this part is white. Otherwise, we should disregard the first bit and start talking about the next bit. Why? Because otherwise it's like each one of them are like 3 to the power of k minus 1 by 3 to the power of k minus 1 grids. So otherwise we should disregard the first digits and consider the next digits, right? So this is how we will move on. For example, if we are talking about these parts, for example, one of them starts with 1, one of them starts with 2. Well, we should ignore both of them, 1 and 2, and just consider these parts and just consider the next digits. It's like this one, and now we are talking about n minus 1 digits, and again the first third starts with 0, the second third starts with 1, the third starts with 2, and so on. So if you continue this process, when you want to decide if I and j should be a white cell or a black cell, you can say that if the first digit of both of them was 1, then it is a white cell for sure. Otherwise, disregard it and take a look at the second bit. If both of them were 1, then it is a white cell. Otherwise, disregard it and look at the next bit, the next digit. If both of them are 1, it is white. Otherwise, look at the next digit, and so on, right? So by continuing this, we will understand that a cell is white if and only if there is a digit such that both of them are 1. That digit in both of the numbers I and j is 1. So we are talking about cell I and j. For example, it is here, row number I, column number j. We consider I and j in base 3. If in base 3 there was a digit that both of them were 1 in that digit, that cell is white. Otherwise, that cell is black. Okay, that's all in here. Is it clear? Is it completely clear? So you should consider I and j in base 3. If the first digit of both of them was 1, they are white for sure. Otherwise, you should disregard the first digit and consider the next digits and move on like this. Okay, so for example, let me tell you an example. For example, in this case, assume that, in here, let me also zoom in. In here, the number of rows, I will enumerate all the rows with numbers from 0 to 9. This is 0, 1, 2, and so on. I write them in base 3. Let's write them in base 3. This one is gonna be 0, 0. This one is gonna be 0, 1. 0, 2. They are all ternary numbers. They are all in base 3. 1, 1, 1, 2, 2, 0, 2, 1, 2, 2. And the same here. This one is 0, 0, this one is 0, 1, and so on. I'm saying that if both of the column and the row, both of them start with 1, then it means that that cell is definitely white. For example, if we talk about this cell, for example, this is at row 1, 1 and column 1, 2. Both of them start with 1. So this is for sure white. Why? Because as I said, the first third starts with 0, the second third starts with 1, the third starts with 2. And the same for columns. The first third starts with 0, the second third starts with 1, and the third starts with 2. So if both of them start with 1, it means that we are in this part, in the middle part. So it's definitely white. Otherwise, if for example it is some number in here, we can look at this part separately and consider that now we have n-1 digit. Again, we can enumerate all the cells from 0, 1, 2, and this here 0, 1, 2. So we can disregard the first digits and look at the next digits. So when we are talking about cell I and j, if we want to find out if this is a white cell or a black cell, we can just consider their first digits. If the first digit of both of them was 1, the first digit of both of them was 1, we can say that it is a white cell. Otherwise, if at least one of them was not 1, then we can disregard the first digit and consider that we have two n-1 digit numbers and then solve it recursively for n-1 digits. So again, we consider the first bit. If both of them are 1, the answer is white. So for example, in here, again, this one is 1, this one is 1. Both of them start with 1, so it is white. So in here, it's like we're talking about cell 1 and 1. Both of them start with 1. Both of them have 1 digit and start with 1. So it's going to be a white cell. So we have two numbers. If the first digit of both of them was 1, the answer is white. Otherwise, remove the first digit of both of them and repeat this process. If the strings, if the numbers became empty, then the answer is black. That cell is black. But if you found someplace that both of them were 1, then that cell is white. Right? Is that okay? Yes, this is also the same recursion idea. But, you know, by seeing base 3, you can simply find out how the cells work. It can also be solved like, yes, it can also be, you can also brute force and implement everything. But my solution is more theoretical in here. Does this make sense? Yes, exactly. If in any bit, if in any digits I and j are both 1, that cell is white. Otherwise, that cell is black. Okay. So for example, if you see this, what is the number of row? Or for example, consider this. In here, the number of row is 2, 1. The column is 2, 1 as well. You see that the second digit is 1 in both of them, so it's white. In here, column is 2, 1. Sorry, row is 2, 1, column is 1, 1. The second digit is 1. In here, the row is 2, 1, column is 0, 1. The second digit is 1 in both of them, so it works. In here, for example, row is 1, 2, column is 1, 1. The first one is 1, 1 in both of them. So if there was some digit that both of them were 1, the answer is white. I mean, that cell is white, otherwise that cell is black. So my theorem is this. I'm saying that if you write I and j in base 3, if both of them had 1 at some digits, the answer is that cell is white, otherwise that cell is black. Does this make sense? And you can see the solution here too. I just have a tb2 base 3 for int x that returns base 3 representation of x. And then I have it for an I and j. A and b are the ternary representations of I and j. And then I just find some bits that both of them are 1. If there existed, then that cell is white, otherwise that cell is black. Okay. In recursive function during n, yeah, that can also work. Maybe I can show you that as well. So that's, yeah, what Dimitri is saying is that we can just generate the answer for n. Maybe we can do it like this: a vector of strings of, for example, gets int n, for example. And if n was equal to 1, here let's have vector of string of results. If n was equal to 1, rest that pushback, for example, only one black cell, return rest. Otherwise, let's have some TMP. Let's have some TMP equal to get of n minus 1, and then we can do it like this. For int I equal to 0, I less than TMP dot size I plus plus. In rest, we should push back rest of I, rest dot pushback. No. Yes, rest dot pushback TMP of I, rest of I. Now we should have 3 copies of TMP of I. You see, it is just pure implementation. I should have 3 copies of TMP of I. So for int TMP, okay, rest of I plus equal to TMP I, rest of I plus equal to TMP I. Okay, and then again I do the same thing. This time in the middle one, this is 1 and 1. In the middle one, I should make everything to be white. Okay. In here, I should just make everything equal to be white. J equal to 0, j less than TMP of I dot size, j plus plus, TM rest of I plus equal to white. And return rest. I think it should work. So you can do this with recursion as well. This is more implementation, less theory but more implementation. So you can just have TMP in the first parts, in the top third. You push back, you have TMP 3 times. Then in the second part, first you have TMP, and then you have everything white, and then you have again TMP, and then in the last part you have TMP. Right? So I think it should work. Let me check this out. Res equal to get of n for int I equal to 0, I less than rest dot size. Let's see if it works. What was the round number? There is some. vector of string. Okay, 1 works for sure. 2, something is wrong. Oh, I have to say this. I made a mistake. I plus 2 times TMP size and I should say that if n equal to 0, 0, 1, 2, 3. Now let's submit it and see if it works. Okay, was it clear? Yeah, rest that back would work as well, right? Yeah, it gets accepted. So yeah, now I implemented it with just recursion without any theory. I just say that if n was equal to 0, vector pushback hashtag, and then get of n minus 1, and then rest that pushback TMP of I, rest of I plus, you know, what I'm saying is that in the first part, we have 3/3, right? I solve it for n minus 1 first, and then I say that we have 3/3. Let me write it like this. In the first third, I just, everything that I have in TMP, I just copy it 3 times. So in here we have TMP, in here we have TMP, in here we have TMP. Okay. In the second part, first I have TMP, then I have everything white, as you see in here, then again I have TMP. In the third, first again I have TMP, then this is the index of that row. I could also say rest dot back, as Dimitri mentioned. In the third I can say TMP, TMP, TMP. So this is how I'm generating. This is just generating, like, we're just doing brute force, and this is just, I mean, implementation, and we're just doing it as it wants. But the other solution that I mentioned was more theoretical. It is easy to show that some cell is white if and only if the ternary representation of both numbers have 1 in a digit. Okay, so in the other solution, let me show you my other solution. In the other solution, we just simply, as I said, we have a 4, and we see if both of them are 1, then it is white. Otherwise, it is black. Are both of the solutions clear? If you have any questions about any of the solutions, feel free to mention that. Otherwise, we can move on to the next problem. Okay, we should move on to problem D. Second one, you mean the implementation one? Or no. In my definition, I have a vector of strings. So I have several strings. Each string represents 1 line. Okay. So each member, each element of my vector is for 1 row. Now I have TMP, I have a 4 to size of TMP. In these rows, in these first rows, I just push back TMP of I because it is exactly like TMP, but I copy it 3 times. So for all the rows in the first third, I copy TMP of I 3 times. Then in the second third, I have TMPI in row number I have TMPI, and then I have everything white, and then again I have TMPI. And then in the third again, I have in row number I have 3 copies of TMPI. So this is how it works. So I have a 4 on all the rows. In the first rows, for example, in row number I, it is exactly like row number I of TMP. I just need to copy row number I of TMP 3 times. Then again I have a 4. Now row number I plus TMP dot size. I'm talking about row number I plus TMP dot size. This row will have TMPI. Then it has everything white. Then again it has TMPI. Again, we have another 4 on I, and everything is 3 copies of TMPI. Cool. So this is how it's going to work. This is the implementation. So there are 2 solutions basically for this problem. One of them is theoretical, more theoretical. One of them is more implementation. And it's it depends on you that which one you're more convenient with. Some people are more convenient with thinking and coming up with theoretical idea and just implement an easier code. Some people are more comfortable with just start implementing the harder code and do not solve theoretically. Both of them are okay. I mean, it depends on what is your style. But both the implementation and theoretical ideas. One of them, theoretical part is harder. One of them, the code part, the implementation part is harder. Okay. Problem D. Okay, for a positive integer n, let v of n. And guys, let me also ask you, how many of you solved C in the contest? Which ones of you solved C in the contest? I just want to have some statistics. If you solved it, put a plus. If you didn't solve it, put minus. I just want to see what is the rate between the ones who solved it and the ones who didn't solve. Okay, cool. Now, have you solved problem D as well? For problem D, if you solved it, put a plus. Otherwise, put a minus. Mustafa, you didn't understand the solution for problem C, or you mean in the contest you didn't understand? Okay, Dimitri, solve D. Yeah, sure, I will do some tutorials on game theory. Oh, I see. Nice. Okay, awesome. So let's discuss problem D. In problem D, for positive integer n, let v of n be the integer formed by concatenating n exactly n times. More precisely, consider n as a string, concatenate n copies of it, and treat the result as an integer to get v of n. For example, v of 3 is 3, 3, 3. v of 10 is 10, 10, 10, 10, 10 times 10. Find the remainder of v of n divided by this prime number. Well, it just says that consider we have some number n, concatenate n times. So we have n n's, right? It's like we have n n's. Just concatenate it right after each other. For example, here we have 10 10s. Or if it was 5, we had 5 5s like this. We just concatenate n to itself n times. And you have to say that what is it modulo that prime number. So in this problem, I have a solution that calculates everything like this. I say that I have to concatenate n times. So I try to find out what happens if I concatenate n 2 to the power of I times. For each I want to find out what is going to happen if I concatenate n 2 to the power of I times. What is this value modulo R mod? Okay, so for each 2 to the power of I want to understand it, and if n had that bit, if the binary representation of n, for example, is like this, for example, in these bits, I just need to add this value, but with some shifting. What do I mean by shifting? I mean that, for example, the next time that I will add it, for example, in here, there are 2 to the power of 0 n's, so there is 1 n. In here, there are 2 to the power of 3 n's, 8 n's. These 8 n's should be shifted. How much should they be shifted? I mean, it's like we should add some zeros at the end of them, right? It's like there's some zeros at the end of them. So they should be shifted. How much? As much as the binary, as the number of digits that n has. For example, if n in base 10 has 3 digits, this number should be shifted 3 times to the left. And then we have 2 to the power of 5. So we have to add 32 n's here. How much they should be shifted? We know that we have 9 n's already. We have 9 n's. Okay, so everything will be shifted 9 times to the left, these ones. Or there is also another solution. We can also say that when 2 to the power of 3 comes, we have 1 n here, shift that 1 n to the left and add 2 to the power of n to 2 to the 3 n's to the right of it. So 8 n's will be added to the right of it. And then when you want to add 2 to the power of 3 to the power of 5 n's, again shift everything as we have to have 32 n's. Calculate that how many digits they have. It's going to be equal to 32 times the number of digits of n in base 10. Shift the current number that much to the left and then add 2 to the power of 5 n's. You solve this another way? Yeah, it's good that you also explain your solution. We'll discuss your solution as well. Great. So this is the general idea. This is what we want to do. So for each 2 to the power of I, we want to see what happens if we have 2 to the power of I n's. And then we should just handle shifting numbers, and this way find the answer. So it works literally like this. We have n, we see in n, and we just have get of n. This modular mode is not needed as well. It is remains from before. So in get of n, initially we have some number n. A is, you know what I want to do? A is currently 2 to the power of 0 n's. 2 to the power of 0 n's. Okay, so initially A is 2 to the power of 0 n's. So there's only 1 n in A. And I have it modulo mode because I have to calculate everything modulo mode. So at the end, my result is modulo mode. So this modulo mode is necessary so that we don't have overflow. But A is n. That modulo mode is just for calculating the answer, because the answer should be calculated in modulo mode. You will see how this doesn't make any issue. So just consider that A is 1n. P means that how many digits do we have right now? Our number of digits, it just shows us how many digits do we have, and just shows it in base 10. I mean, it just shows 10 to the power of the number of digits of A. For example, if your A is 37, your P is gonna be 10 to the power of 2. It's gonna be 100. Because it has 2 digits, it's gonna be 10 to the power of 2. So as you see the code here for this D10, each time while n divided by 10 res equal to res times 10. That modulo mode is again for calculating, because at the end we have to calculate everything modulo mode. That is the reason that you have modulo mode here. But anyways, it just means that D10 means that how many digits A has, just consider 10 to the power of that. Okay, if your A is, for example, 574, what your P will be? Can you say what D will be if A is 574? Can anyone say that? For example, if A is 574, what P will be? It's not hard, guys. Let's see who can say it. Exactly. No. It is 1,000. I say that see how many digits P has. P has 3 digits here, right? See how many digits P has. It has 3 digits. Consider 10 to the power of that number. So it's gonna be 10 to the power of 3. It's gonna be 1,000. If you see this code, also each time while n equal to n divided by 10, res equal to res times 10. For example, if you have 574, each time res starts with 1, each time you remove 1 digit from here and add another 0 to res. Again, you remove 1 digit here, add another 0, so your number starts with 1, you have 3 digits, so 3 times 3 digits will be removed. And when these digits will be removed, res will be multiplied by 10. So how many times res will be multiplied by 10? Equal to the number of digits that n has. So if n has, for example, x digits, res is gonna be 10 to the power of x. So P is 1,000. And B is equal to n as well. B just shows that how many n's do we have to have. Okay, so we need to have b n's, right? And b is equal to n. Okay, so b is just an additional factor. I could also work with n, but I just wanted to work with a and b. So I want to have b copies of n. I want to concatenate b n's. The number of n's is b. Okay, and b should be equal to n. B could be something else as well, but I want it to be, but in this problem, b is equal to n. We want to have n concatenates of n. So, I say while b, it is very similar to power. If you have, you have already implemented power a to the power of b, it is very similar to that. The solution in this one is very similar to that. I'm just saying that while b, if b was odd, it means that if b and 1 means, if b and 1 means that if the last digit of b was 1, it means that whatever a is, we can append a to the end of res. So res will be, as I said, p is equal to the number of digits that n has or a has already. Because we see that p will change. As a change, p will change as well. So p is the number of digits 2 to 10 to the power of, let me say it like this, 10 to the power of the number of digits of a. So p is 10 to the power of the number of digits of a. A is n initially, so p is going to be 10 to the power of n initially, 10 to the power of the number of digits of n. In here I say that if b was odd, res will be equal to res times p, because I should shift res p times, we should see how many digits a has. That much we should shift a to res to the left and add a to the end of it, right? So if a has x digits, res should be shifted x times to the left and a will be added to the end. So res will be equal to res times p. P is 10 to the power of the number of digits of a. So it's like as much as many digits that a has, we are adding 0 to the end of res. First, we see that how many digits a has. We open that space for a. Okay, so p is the number of 10 to the power of the number of digits of a. So when we multiply res by p, it's like we are opening that space in the end for a. And then we add a to there, right? So we see that how many digits a has, we open that space for a, and then we add a there. And then we say that a, now we want to have a is right now 2 to the power of I n's. We want to make it 2 to the power of I plus 1 a's. In order to do that, a first should be a times p. I want to, if right now a is 2 to the power of I n's, for the next step I want to make it 2 to the power of I plus 1 a's. In order to do that, I just say that a is equal to a times p plus a. So I open a space for a at the end, and I concatenate a to a. And then p will be multiplied by itself, because if previously we had x digits, now we have 2x digits. So if previously we had 10 to the x, now we have 10 to the 2x. So p will be multiplied by itself and b will be divided by 2. Because now we have to talk about the next digit and see if that is 1 or 0. It might be a bit complicated if you haven't previously implemented power, a to the power of b, in O of log, in theta of log. This is the non-recursive version of power. It is very similar to that. So if you haven't implemented that, it might look a little bit complicated. But this is how we can solve this problem. And also, Dimitri, you said that you have another solution. Maybe you can also tell me about your solution. Maybe I can also explain your solution. Is this solution clear? Did you guys understand it? If you have any questions about this one, you can say it right now. And if you want me to move on to the next problem, you can say this. My solution for each digit computes its contribution to that huge number modulo m. Okay, for each digit, how does that work? For each digit. To the power of Yeah, I see. And how do you calculate that value, 10 to the power of 0 plus 10 to the power of 2 plus 10 to the 4? Hmm. Geometrical progression. Yes, that can be done. Yes, you're right. That can also work. Yes. Yes, with a little bit of algebra that can be worked. That's geometrical progression. And you could also do that. Yeah, that is again mostly a mathematical solution. If you use algebra, yes, you're right. This is also an interesting idea. For example, if n is, let's consider 23, for example. You can say that for this 3, we have 3 times the effect of this 3 on the answer is 3 times 10 to the 0 plus 10 squared plus 10 to the 4th plus 10 to the 6th and so on, right? 2, it goes on. And for this 2, we have 2 times 10 to the power of 1 plus 10 to the power of 3 plus 10 to the power 10 to the 5th and so on. These values are geometrical progressions, right? This problem is problem D. The next problem is problem B. And yes, we have to calculate this value, and each time we can multiply it by 10 and we have the answer. And it is easy to calculate this value. You know, in general, we can say that p to the power of 0 plus p to the power of 1 plus 2 p to the power of k is gonna be equal to p to the power of k plus 1 minus 1 over p minus 1, right? So in here, it's like our p is 10 to the power of 2. So we have p to the power of 0 plus p to the power of 1 plus p to the power of 2 plus p to the power of 3 and so on. Okay. To the last one is 10 to the power of 2 times 22, 44. And this one goes to 10 to the power of 45. We have 46 digits in total. It starts from 0 and ends at 45. So this is gonna be equal for p equal to 10 to the power of 2. So this is gonna be equal to p to the power of k plus 1. So p is 10 to the power of 2. In here we have 10 to the power of 2 to the power of 22. So it's gonna be 10 to the power of 2. Can you see this? I think you can see this here. Let me write it here. We have 10 to the power of 2 to the power of 23 minus 1 over 10 to the power of 2 minus 1, right? And this can be multiplied by 3, and each time and the next time multiply it by 10 and then multiply it by 2 and add these values, and this is going to be your answer, right, Dimitri? Is it exactly like this? Hello, Asif. How are you doing? Yeah, awesome. Yeah, that is also a very beautiful solution. It is more mathematical. Oh, I'm doing fine as well, thank you. Thank you very much. I was sick last week. I still am a bit sick. I don't know why. I don't know why I don't get well completely, but yeah, I'm very better now. Okay, so I think we can move on to problem E, right? Are everyone okay with problem D? If you have any questions about it, just tell me. Thank you very much. Thank you. Okay. Problem E. Reachability. Okay. Have you solved A to C massive? For problem E, reachability in functional graph. Let me tell you this statement first. There is a directed graph with n vertices numbered 1 to n and n edges. The out degree of every vertex is 1 and the edge from vertex I points to vertex AI. Counts the number of pairs of vertices u and v such that vertex v is reachable from vertex u. So we have a special graph. In this graph, the out degree of each vertex is 1. Out degree is always 1. So each vertex goes to exactly one other vertex, like this. You have to say that how many pairs, ordered pairs, like u and v do we have, such that there is a path from u to v, such that you can start from u and go to v. You have to say this. How many of you guys have solved this problem in the contest? Well, see. Awesome. Dimitri, how many problems you solved? And where are you from, Dimitri? Guys, all of you, where are you from? Oh, okay, it was us. I see. Good, it's very good. Where are you guys from, all of you? Vasif is from Pakistan. Dimitri from Russia. Ankal from India, I guess. Awesome. Awesome, everyone. Dimitri, maybe it won't be bad if you message me in Discord. Maybe are you interested in doing streams? Because I think you have solved good number of problems. Are you interested? If you want, you can tell me. So for this problem, we want to find the number of pairs like u and v such that u has a path to v. Well, first of all, my idea was this. First of all, when the out degree of each vertex is 1, then we can be sure that our graph looks like this. There are some cycles and some vertices go to these cycles. So it always looks like this. It's like we have some cycles in the middle and some vertices have a path to these cycles. This is the shape of our graph. Some cycles in middle, the other vertices are pointing out to these cycles. So this is the shape of our graph for sure. Okay, so several cycles and some vertices going to those cycles. If the in degree was also 1, if both out degree and in degree of each vertex was 1, then our graph was simply several cycles. If the out degree and in degree were both 1. But in here, only out degree is 1. So it looks like this. If only in degree was 1, we had several cycles and many edges to outside. If only in degree was 1. Okay. In here, out degree is 1. So it's like this. And if you see the examples, you can also see that. For example, in the first case, we have 1 has h to 2, 2 has h to 1, 3 has h to 1, and 4 has h to itself. In here, as you can see, we have 2 cycles. One cycle is between 1 and 2, and one cycle is for itself. And 3 points out to this cycle. Okay, we could also have some vertex 5 in here, some vertex 6 in here, some vertex 7 in here, and some vertices 8, 9, 10 as another cycle in here, and for example 11 like here. So anyway, it's gonna be several cycles and several vertices pointing out to those cycles. This is the shape of the graph. Yes, self loop is also a cycle. Yes. So this is the shape of our graph. Now we want to see that with this situation, what is the number of pairs that they have a path to each other. Well, first of all, we have several cycles, right? For each cycle, if it has s vertices, you know, in general, I want to find res of I. Res of I is the number of vertices that I has a path to. So res of I is the number of vertices like j such that I has a path to j. Okay, so res of I says that how many vertices are reachable from I. Okay, first of all, for all the vertices in cycles, if there are s vertices on the cycles, each vertex, the res of each vertex in this cycle is s. For each vertex I, res of I is equal to s. Is equal to s. Why? Because each vertex in this cycle only can reach all the vertices in the cycle. It can reach itself and all the other vertices in the cycle. So it can reach the s vertices on the cycle. So all the vertices in our cycles, if the size of their cycle is s, they can reach s vertices. So they can only reach vertices on their own cycle. Is that clear? This is the first thing to say. The second thing is that for all the other vertices, it's like they have a parent, and their answer is gonna be equal to the answer of their parent plus 1. You know, for each other one of them, for example, like v, you can assume that a of v is their parent. Res of v is gonna be equal to res of a of v plus 1. Because whatever that vertex can reach, this vertex can reach as well. Also, it can reach itself. So v can reach itself and everything that its parent can reach. For each vertex v can reach itself and everything a of v can reach. Yes, exactly. Exactly. For each node in cycles, dp of u is equal to length of the cycle, and otherwise dp of u is equal to dp of parent of u, or dp of a of u plus 1. Exactly. So this is everything that we can say in here. So we can just say that we have, first we get everything, and first I have some DFS1 that I find the cycles. Okay, so in DFS1 I want to find the cycles and see that in which cycle each vertex is, if it is in a cycle. If it is in no cycle, cycle of I is gonna be equal to -1. Otherwise, I have one vertex of that cycle as the indicator of that cycle. So let's see how it works. So DFS1, I say that first, when I want to find a cycle, as I said, psych of v, or psych of I is equal to the cycle that vertex is in it. And I just consider the index of one of those vertices as the index of that cycle. So psych of v is gonna be equal to one of the vertices in the cycle that vertex is in it. So first of all, I say that I have some v's, which is short for visited, and I have two values for it. It can be either, other than 0, it can be 1 and 2. 0, if v is 0, it means that vertex is not visited yet. If it is 1, it means that is visited and it is still open. Okay, so this means that it is not visited. This means that it is visited and it is still open. So we have not closed its DFS. And it is 2 if it is visited and it is closed now. I mean, we're done with its DFS. It is closed. If you see initially, when I enter a vertex, I set vis of v equal to 1. And when I want to close their DFS, I set the vis of v equal to 2. So when vis of v is, if vis of v is equal to 1, it means that DFS is open, DFS of that vertex is open. If it is 2, it means that DFS of that vertex is closed. Okay. So how is that useful? Why it is useful? Why is it useful to know that if that DFS is open or closed? You will see it right now. When I want to find cycles, that is going to be important. In DFS1, first, I say that, as I said, vis of v equal to 1, because the DFS is open right now. If vis of a of v was 1, okay, v has an edge to a of v. If vis of v is 1, it means that DFS of v, a of v, is open right now. It means that we were in this DFS, and this DFS is not closed yet. We went forward, and we reached v. It means that we found the cycle. If visited of a of v is 1, it means that its DFS is still open. So we started from a of v. We haven't finished its DFS yet. We haven't closed it. So a of v has reached v. There is a path from a of v to v. And then v has an edge to a of v. It means that we find the cycle. Okay, so if vis of a of v is 1, it means that we found the cycle. But if vis of a of v is 2, it means that a of v is visited before and its DFS is closed as well. It has visited some vertices and it is closed. Now v only has an edge to a of v. This way v is not in any cycle. But if vis of a of v is 1, it means that vertex is also, these two vertices are in a cycle. So if vis of a of v was 1, we can just say that we set int of x equal to a of v. X is the index of that cycle. I set this vertex as the index of the new cycle. Okay, so for all the vertices in this cycle, I'll set a of v as the index. I said that, okay, they are in the cycle that has a of v. Okay, so a of v is the candidate, is the index of that cycle. I set int of x equal to a of v, and psych of v is gonna be equal to x. And I will explain this line later. You will see why this line exists. I set psych of v equal to x. For now, forget about this line, and vis of v equal to 2 and return x. If vis of a of v was 2, psych of v is gonna be equal to -1, because it means that DFS of this part is closed. DFS of this vertex is closed. And v is in no cycle. So this way we can say that psych of v is equal to -1, vis of v equal to 2, close the DFS and return. And in here, we can say that otherwise it means that visitor of A of V is 0. It means that that vertex is not visited yet. So if that happened, we see that with DFS1, we see DFS1 of A of V, and we get it as X. Okay. So X can be -1 if A of V was in no cycle, or it can be the index of that vertex that is in the cycle. And I can say that cycle of V is equal to X, and now we reach this line, which is very similar to this line. I say that if X was equal to V, for example, when I come back from this vertices, cycle of V will become equal to A of V. Cycle of this vertex will be A of V. Cycle of this vertex will be A of V. Cycle of this vertex will be A of V. And so on. When I reach A of V itself, when I reach a vertex that V is equal to X, it means that we're done with the cycle. We found all the vertices. A of V is the outgoing edge from V. V has an edge to A of V. Yes, A of V is our graph. A of V is the outgoing edge of V. Okay. So we write A of V on each of these vertices. And when we got back to A of V, it means that we're done with this cycle. So if the previous vertex was here, for example, maybe the DFS of A of V is called by a vertex in here. That vertex is not in the cycle anymore. So when we got to A of V itself, when X became equal to V, when we got to the vertex that is the index of the cycle, now we should set X to be -1. Because now we don't have any cycle anymore. We reached the end of it. We reached the end of the cycle. Right? Yeah, adjacency list is not necessary because we have only one outgoing edge. There is only one outgoing edge, so it's just enough to have some A of V. If you define adjacency list, each one of them have exactly one member, right? It's like you have some vectors, the size of each vector is 1. So you could also have a number instead of that, right? So yes. As I said, when we reach A of V, we don't have a cycle anymore and we can just come back, right? We can just set X equal to -1 because these vertices are in no cycle anymore. These vertices will be -1. They are in no cycle. And the line is here for this exact same reason as well. Maybe A of V is equal to V. Sorry. Maybe A of V is equal to V itself. Then we just set cycle of V to itself, and then if X was equal to V, set X equal to -1 for the other vertices that have an edge to this one. And then we return X at the end. And this is how we can find all the cycles. Is this part clear? So this is how we find the cycles. Now, after we found the cycles, sorry, I say that if cycle of I was not equal to -1, if it was in a cycle, size of cycle of I plus. So this is the parts that I find out what is the size of each cycle. Okay, if cycle of I was not -1, size of cycle of I plus. And then I say memset with 0 size of V's because I want to do another DFS. Okay, I set all the visitors equal to 0. In this second DFS, I have a 4i0 to n. Let's see how this second DFS works. if not of with of I, dfs2 of I. In dfs2 I will calculate rest of I. How many vertices are reachable from I. How do I do that? I just say that in dfs2, I say that initially with of v equal to 1 because we visited this vertex if psych of v was greater than or equal to 0. It means that this vertex is in a cycle. If that vertex was in a cycle, we just say that rest of v equal to size of psych of v. As I said, if this vertex was in a cycle, then result of v, rest of v is equal to the size of cycle of v. Okay, as we said, because if it is in a cycle, the answer of it is going to be equal to the size of the cycle. Otherwise, if it was like this, I will return. Otherwise, I say that if a of v was not visited yet, first dfs2 of a of v, and then set rest of v equal to rest of a of v plus 1. Okay, so if it was not visited, dfs2 of a of v, and then rest of v is going to be equal to rest of a of v plus 1. This editor is atom. Yeah. So if it was not visited, if a of v was not visited, we can just say that it is equal to dfs of. We run dfs2 on a of v, and rest of v is going to be rest of a of v plus 1. Yeah, that's completely okay. And this was problem E. It was a hard problem. Make sure to implement it now. It really helps. You know, it's so important to solve contests. There are some problems that you don't solve during the contest. It's so important to make sure that you accept them after the contest. So important. You're welcome. You're welcome. Okay. So this is how this one will work. Sorry. Is it clear for everyone? Shall we move on to the next problem, problem F, or? Yeah, you're welcome. Make sure to implement it. Okay, I guess now we can move on to problem F. You are given sequences of length n, a equal to a1 to an, b equal to b1 to bn. You are also given q queries to process in order. There are three types of queries. 1 LRX, add x to each of AL to AR. 2 LRX, add x to each of BL to BR. 3 LR prints the remainder of sum of AI times BI when divided by this much. Okay, so you have three types of queries. The first query, add an interval in A. The second type of query, add an interval in B. The third type of query gives you an interval and says that if you multiply these values one by one, what is the answer? Has anyone solved this problem during the current test or afterwards? Sure. Has anyone solved it? Well, in this problem I used segment tree and lazy propagation. So I used lazy propagation of segment tree. So if you're not familiar with those terms, maybe this problem is not yours for now, and maybe you should solve it later in your journey. For now, you can skip this problem if you're not yet familiar with segment tree or lazy. But otherwise, let's discuss the solution. In this problem, first let me explain a little bit. You know, when I have to add x to an interval, of a, for example, I have to add x to an interval of a. I can just go, assume that for each node I have 5 values to be precise. For each node in my segment tree, I have 2 values of val. Val of 0 is for a's, val of 1 is for b's. Lazy of 2, again, lazy of 0 is the lazy for lazy of 0 is the lazy for a's, lazy of 1 is the lazy for b's, and also mul, which is the multiplication of these 2 intervals one by one and sum of those multiplications. So each interval, each node of my segment tree, each interval, I have these values. I have these 5 values. I know that what is the sum of a's in that value, what is the sum of b's in that value, what is the lazy of a's, I mean how much each value should be added, that I should shift if I go to the children, what is the lazy a, what is lazy of b, and what is the answer if I multiply all the a's and b's in this interval and sum them up. I have all these values, okay? So now, when I want to add x to all the a's in some, for example, nodes, in a node, assume that I want to add x to all the a's. Well, this way, the sum of a's will be added by the length of segments times x. Lazy will be added by x, and mul will be added by x times sum of b's. Because whatever the sum of b's in that node is, I should multiply x by that, because each one of them, I mean when each a of i's will be added by x, it's like I'm adding x times that corresponding value of b to my answer. So when I'm adding x to some value of a, it's like I'm adding the corresponding value of b times x to my mul. So x times b should be added to mul. Does it make sense? Is it clear? So this is how it works. So now, when I have these values, I just need to find out how I can find these values, right? Well, as I said, it's just a simple lazy. Each time I just need to make sure that I will shift everything when I go downwards. And whenever I reached a segment, I reached a node that I wanted to change its value, I just need to add x to one of my numbers, either a or b, and the lazy of it, and the mul should be added by x times the value of the other value in that node. For example, if I'm adding x to a, I should add x times b, right? So in each node, I have the sum of a's, I have the sum of b's, and I have the sum of multiplications, the sum of products. So in here, I can just say that first, initially, I get n and q, and I see in ai, see in bi, this add function just adds ai and bi in that specific cell. Let's first explain add function and see how it works. When I add x, and id means, if id is 0, it means that a's will be added. If id is 1, it means that b's will be added. Okay. So I'm talking about L and R. I have some ID, I have some X, V, S, E. If this interval was completely outside of my node, just return. If this interval, this node, is completely inside my query interval, I just add node V, S, E, X. I just add X to ID of this node. Okay, ID is either 0 or 1. It means either A or B. I just add to ID the element number ID x in this node V, which is from S to E. Let's see how it works. Add node works like this. When I want to add x to ID, I just say that seg of v dot val of ID is equal to seg of v dot val of ID plus 1 LL times size of this segment times x. Size of this segment times each one of them should be added by x. So the sum will be added by e minus s times x modulo mod. Okay, so seg of v dot val of id is equal to seg of v dot val of id plus 1 LL times each one of them will be added by x. So e minus s, which is the size of that node, times x modulo mod. Seg of v dot lazy of id will be added by x, and seg of v dot mol will be equal to seg of v dot mol plus 1 LL times x times seg of v dot val of the other index. So I just have if I'm adding to a, I just see that what is the sum of b's, and I add that value times x to my mol. Okay, so this is how it works. Seg of v dot mol will be seg of v dot mol plus 1 L times x dot times seg of v dot val of I. So I add this node and then I shift my node for lazy propagation, and my shift works like this. I see the left child and right child. I have a 4 on 0 and 1 for values of a and b. I add LCS mid I use this function add node again. Seg of v dot lazy of I should be added to index I in this node and also in this node, and seg of v dot lazy of I is equal to 0 then. And then I just update the children. If I'm not done here, I will break my segment into the two children, and seg of v dot val of I will be equal to this, seg of lc dot val of lc dot val of I plus seg of rc dot val of I, and mol it will be equal to this. Mol will be equal to the sum of the mols of these two children. Okay, so this way I will update all these values. I mean, I add children, and then when I was back from children, I will update the parents as well. And then in get, this is how I do add. I do addition. In get, I have some values of L and R. If this segment, this interval was completely outside of my query interval, return 0. If it was completely inside of my query interval, return seg of v dot mol. I have the sum of these mols. I will just return that. Otherwise, I should first shift, and then I just find the answers in the left node, left child, and in the right child, and I will sum them up and return them. And this is the way that I can find out the answer. And this way, I can print everything. So I use lazy propagation of segment tree. And for each vertex, I mean for each node, for each interval, I keep these 5 numbers and I can easily update them. And I just need to make sure that whenever I pass over a vertex, I will shift everything to their children. And I also use this add node function that makes everything very, very cleaner. Just val will be updated, lazy will be updated, and mol will be updated according to seg of v dot val of not of id, the other sum. Okay, is this one clear? If you guys have any questions about this part, this problem, you can say. Otherwise, I think we're done with the contest. Okay, you're welcome. You're welcome. So I think I'll see you in the next live streams. Thank you very much for watching. I hope you enjoyed it and you learned something. Thank you. I will see you next time. Is tomorrow any contest? I think at Coder was not, but maybe we had a CF contest. Yes, we have a sea of contests. So that contest will be for sure streamed as well, either by me or Yan or Ahmed. So see you tomorrow. Thank you very much for joining. Goodbye.